April 24th, 1990. Aboard the Space Shuttle Discovery, astronauts carefully release a school bus-sized cylinder into orbit, 547 kilometers above Earth. It's the Hubble Space Telescope, the product of decades of planning, engineering, and political fighting to get it funded at all. Mission controllers back on the ground expect the first images to be the sharpest views of the universe humanity has ever captured. Instead, the first pictures come back blurry, badly blurry. Within weeks, engineers traced the problem to a mirror ground to the wrong shape, off by a mere 2.2 microns, roughly 1/50th the width of a human hair, but enough to ruin the telescope's focus entirely. It will take 3 more years, and a dramatic 1993 shuttle repair mission where astronauts install corrective optics, essentially glasses for a telescope, before Hubble finally delivers on its promise. It's a strange, humbling start for what would go on to become one of the most productive scientific instruments in human history, and the direct ancestor of an even more powerful telescope, launched in 2021, that would eventually take over the task of showing humanity the universe in resolution nobody thought possible. This is how these two machines actually work, and why building a telescope that can see to the edge of the observable universe turns out to be one of the hardest engineering problems humanity has ever solved. Fast forward to December 2021. In a mission operations room at the Space Telescope Science Institute in Baltimore, systems engineer Mike Menzel is watching a live telemetry feed, along with dozens of colleagues, as the James Webb Space Telescope, roughly a week into its month-long journey toward L2, begins the single most nerve-wracking phase of its entire deployment, unfolding its primary mirror. Unlike Hubble, whose rigid one-piece mirror was fully assembled before launch, Webb's 18 hexagonal mirror segments had to fold up like a piece of origami to fit inside its rocket fairing, and now, drifting in the vacuum of space, they needed to unfold, lock, and align themselves with almost no room for error and absolutely no possibility of a repair mission if anything jammed. Engineers in the room had rehearsed this sequence hundreds of times using ground-based test models, but this was the real telescope. $100 million and more than 2 decades of work riding on a sequence of motors, hinges, and latches performing correctly, one after another, roughly 1 million kilometers from the nearest human hand that could ever reach them. Menzel would later describe the deployment period as the scariest part of the entire Webb mission, not because any single step was especially complicated on its own, but because Webb had roughly 344 individual points, where something could fail badly enough to end the mission entirely, none of them fixable after the fact. When the final mirror segment locked into place on schedule, the room didn't erupt into celebration the way mission control often does in movies. Engineers described a quieter, more exhausted relief, the sense of having successfully threaded a needle that had occupied years of their working lives. That moment, 18 individual mirrors, each the size of a coffee table, locking together in the cold and dark 1.5 million kilometers from Earth, is where the real story of how these telescopes actually work begins. Before getting into how Hubble and Webb actually work, it's worth understanding why astronomers went to the immense trouble and expense of launching telescopes into orbit in the first place, rather than simply building bigger telescopes on the ground. Earth's atmosphere, while essential for life, is a genuine obstacle for astronomy. Air constantly moves and shifts in temperature, bending and distorting light as it passes through, the same effect responsible for stars appearing to twinkle to the naked eye. For a ground-based telescope trying to resolve extremely fine detail, that constant atmospheric turbulence blurs images no matter how large or well-built the telescope's mirror is. Earth's atmosphere also blocks large portions of the electromagnetic spectrum entirely, including most infrared, ultraviolet, and X-ray radiation, meaning ground-based telescopes are fundamentally limited to observing only the specific wavelengths of light that manage to make it through the atmosphere in the first place. Placing a telescope above the atmosphere entirely solves both problems at once. With no air to distort incoming light, a space telescope can achieve dramatically sharper resolution than an equivalent ground-based instrument. And free from atmospheric absorption, a space telescope can observe wavelengths of light completely invisible from the ground, opening up entirely new ways of studying the universe. That basic logic, get above the atmosphere, see more clearly, see more wavelengths, is the foundational reason both Hubble and Webb exist at all. Both Hubble and Webb are fundamentally what's called reflecting telescopes, a design that traces back to Isaac Newton's original reflecting telescope, built in 1668, though scaled up almost unimaginably and refined with modern materials and precision engineering. A reflecting telescope works by using curved mirrors rather than glass lenses to gather and focus incoming light. Light from a distant star, galaxy, or planet enters the telescope and strikes a large primary mirror, precisely curved to reflect that light toward a smaller secondary mirror positioned in front of it. That secondary mirror then redirects the light toward the telescope's scientific instruments, cameras and spectrographs, which capture and record it for analysis. Mirrors are strongly preferred over lenses for large telescopes because a mirror can be supported from behind across its entire surface, whereas a large lens can only be supported around its edges, making an enormous glass lens structurally impractical and prone to sagging under its own weight in ways that would distort the image. The single most important factor determining a telescope's power isn't magnification, contrary to popular assumption. It's the diameter of its primary mirror, since a larger mirror gathers more light and, crucially, achieves sharper resolution, meaning it can distinguish finer detail and pick out fainter, more distant objects. This is exactly why the difference between Hubble's primary mirror and Webb's became one of the most important design decisions behind each telescope. Hubble's primary mirror measures 2.4 meters in diameter, made of a specialized glass called ultra-low expansion glass, ground and polished to a precision so exact that if the mirror were scaled up to the width of the entire continental United States, the largest bump or dip on its surface would still measure only a few centimeters. Coated in a thin layer of pure aluminum with a protective layer of magnesium fluoride on top, the mirror reflects roughly 70% of incoming ultraviolet, visible, and near-infrared light toward Hubble's instruments. Hubble orbits Earth at an altitude of roughly 547 kilometers, completing a full orbit approximately every 95 minutes, meaning it experiences a sunrise and sunset roughly every hour and a half. This relatively low orbit was specifically chosen to keep Hubble within reach of space shuttle servicing missions, since it was designed, uniquely among major space telescopes, to be visited and physically repaired or upgraded by astronauts. Between 1993 and 2009, 5 separate servicing missions replaced failing components, installed new, more advanced instruments, and famously corrected that original 1990 mirror flaw, extending Hubble's operational life far beyond its originally planned lifespan and keeping it scientifically productive for well over 3 decades. Because Hubble primarily observes visible and ultraviolet light, wavelengths similar to, though extending somewhat beyond, what the human eye can detect, its images are what most people associate with dramatic space photography: sweeping, colorful nebulae, detailed galaxy clusters, and crisp planetary images that closely resemble, at least in principle, what the human eye would see if it were powerful enough to observe these objects directly, though the specific vivid colors in published Hubble images are typically assigned during processing to represent data gathered through different filters, rather than being literally what a human eye would perceive. Webb, launched on Christmas Day, December 25, 2021, was designed from the outset to answer questions Hubble fundamentally couldn't, and that required a radically different engineering approach across nearly every aspect of the telescope's design. The core scientific goal driving Webb's design was observing the earliest galaxies in the universe, formed shortly after the Big Bang, roughly 13.8 billion years ago. Because the universe has been continuously expanding since then, light from these extremely distant, extremely ancient objects has been stretched by that expansion on its journey to us, a phenomenon called redshift, where light originally emitted primarily as visible or ultraviolet radiation gets stretched into longer infrared wavelengths by the time it finally reaches our instruments. To see the universe's very earliest galaxies, in other words, a telescope needs to be built specifically to observe infrared light, rather than the visible and ultraviolet light Hubble primarily focuses on. This single requirement cascaded into nearly every major design decision behind Webb. Infrared light is essentially heat radiation, meaning any warm object, including the telescope's own instruments and even the spacecraft's own structure, would flood Webb's infrared detectors with interfering heat signatures if not kept extremely cold. Solving this problem required Webb to operate at temperatures below minus 233 degrees Celsius, colder than almost anywhere naturally found in the solar system outside the shadowed craters of the outer planets' moons. To achieve and maintain that extreme cold, Webb carries one of its most visually distinctive and engineering-critical components, a 5-layer sunshield roughly the size of a tennis court, unfolded fully only after launch, made of a specialized material called Captain, coated with reflective aluminum and, on the 2 hottest-facing layers, additional silicon-based coating for extra reflectivity. Each of the sunshield's 5 layers is separated by a small vacuum gap, and each layer progressively blocks and radiates away more heat than the one before it, so that by the time any residual warmth reaches the telescope's mirrors and instruments on the shaded side, the temperature has dropped from roughly 110 degrees Celsius on the sun-facing side down to the required deep cold operating temperature on the far side. An engineering feat frequently compared to keeping an ice cube from melting while sitting a few meters away from a bonfire. This sunshield requirement also directly shaped Webb's chosen orbit. Rather than orbiting Earth relatively closely the way Hubble does, Webb operates from a location called the second Lagrange point, or L2, positioned roughly 1.5 million kilometers from Earth, in the direction away from the Sun. At this specific location, the combined gravitational pull of the Sun and Earth allows Webb to maintain a stable position relative to both, while keeping the Sun, Earth, and Moon consistently positioned on one side of the telescope, allowing the sunshield to reliably block heat and light from all three sources simultaneously, keeping the telescope's instruments in constant, stable shadow. The distance to L2 also meant Webb could never realistically be serviced by astronauts the way Hubble was, unlike its predecessor's relatively accessible low Earth orbit. Every single component of Webb had to work correctly the first time, without any realistic possibility of a repair mission if something failed after launch, a design constraint that drove years of additional testing and redundancy planning throughout the telescope's development. Webb's primary mirror measures 6.5 meters in diameter, more than 2.5 times larger than Hubble's, giving it roughly 6 times the total light collecting area. A mirror this large, though, presented an entirely different engineering problem. No rocket fairing existing at the time of Webb's design was large enough to launch a single rigid mirror of that size into space. The solution was to build Webb's primary mirror, not as one solid piece of glass, the way Hubble's mirror was made, but as 18 separate hexagonal segments, each roughly 1.3 meters across, made of beryllium rather than glass, chosen specifically for its light weight and stability across extreme temperature changes. These 18 segments folded up compactly for launch, then unfolded and locked into their precise final positions once Webb reached its operating location near L2, a process that took roughly 2 weeks to complete after launch and represented one of the most complex, closely watched automated deployment sequences ever attempted in space. Each of the 18 mirror segments is mounted on a set of tiny, precisely controlled actuators, allowing engineers on the ground to make extraordinarily fine adjustments to each segment's position and curvature, aligning all 18 individual mirrors so precisely that they function together as a single, seamless optical surface, accurate to within a fraction of the wavelength of light itself. This alignment process, completed over several months following Webb's deployment, was one of the most technically demanding phases of the entire mission, requiring the telescope to observe a single star, capture the resulting 18 separate, initially misaligned images, and gradually adjust each segment until all 18 images converged into one sharp, unified point of light. Once light reaches either telescope's instruments, having been gathered and focused by the primary and secondary mirrors, the real scientific work begins. Both Hubble and Webb carry a suite of specialized instruments designed to analyze incoming light in different ways, rather than simply producing a single type of image. Cameras aboard both telescopes capture direct images, but often using multiple different filters, each one allowing only a narrow band of wavelengths through at a time. By capturing separate images through several different filters and later combining them, scientists can highlight specific chemical elements or physical processes that would be invisible in an unfiltered single image, and can construct the vivid color. Processed images most commonly published for public audiences, since the specific colors used often correspond to particular wavelengths of light, rather than what a human eye would literally perceive. Alongside cameras, both telescopes carry spectrographs, instruments that split incoming light into its full range of individual wavelengths, similar to the way a prism splits sunlight into a rainbow, but with far greater precision. This spread-out light, called a spectrum, reveals distinctive patterns, dark or bright lines at very specific wavelengths, corresponding to particular chemical elements and molecules present in whatever object the light originated from, whether that's a distant star, a galaxy, or the atmosphere of an exoplanet. This is precisely how astronomers identify the chemical composition of objects light years, or even billions of light years away, without ever physically visiting them. And it's the same basic technique that allowed scientists to detect water vapor, methane, and other molecules in the atmospheres of distant exoplanets using Webb's instruments. Both telescopes ultimately need to transmit their observations back to scientists on the ground. And this final step, while less visually dramatic than mirrors and sunshields, is just as essential to the whole system actually working. Hubble, orbiting relatively close to Earth, transmits its data through NASA's Tracking and Data Relay Satellite Network, a constellation of communication satellites in Earth orbit that relay Hubble's observations down to ground stations, typically within a matter of hours of an observation being completed. Webb, sitting roughly 1.5 million kilometers away at L2, relies instead on NASA's Deep Space Network, a system of large radio antenna facilities positioned around the globe specifically to communicate with distant spacecraft, transmitting its data across that much greater distance using a dedicated radio link, typically downloading its full daily allotment of observations during scheduled communication windows. Once received, raw data from both telescopes goes through extensive processing before it's ready for scientific analysis or public release, correcting for instrument quirks, removing background noise, calibrating brightness and color values, And, for publicly released images, carefully combining and coloring data from multiple filters to produce the polished, striking images most people recognize from news coverage and NASA press releases. It's worth ending on something that often gets lost amid comparisons of Hubble's age against Webb's cutting-edge technology. The two telescopes were never designed to replace each other entirely, and both have continued operating simultaneously since Webb's 2021 launch, each contributing something the other genuinely can't. Hubble's sensitivity to visible and ultraviolet light makes it uniquely suited to certain observations, including detailed studies of stellar processes and phenomena that emit primarily in those wavelengths, that Webb's infrared-focused instruments simply aren't built to capture as effectively. Webb, meanwhile, opens up entirely new scientific territory that was essentially invisible to Hubble altogether. The earliest galaxies in the universe, the detailed atmospheric composition of distant exoplanets, and objects shrouded in dust clouds that block visible light but remain transparent to infrared. Astronomers frequently combine data from both telescopes on the same target, using Hubble's visible light data, alongside Webb's infrared observations to build a far more complete picture of a given object than either telescope could provide entirely on its own. More than 3 decades after that blurry first image in 1990 and the dramatic repair mission that saved its mission afterward, Hubble remains scientifically active today, working in tandem with a telescope more than 2.5 times its size, cooled to a temperature colder than almost anywhere else humans have ever sent a machine, sitting 1.5 million kilometers from Earth, patiently gathering the faint, ancient light of galaxies that formed when the universe itself was still in its infancy. Back in that Baltimore operations room, once the celebrations quieted down and the engineers moved on to the months-long process of aligning Webb's 18 mirror segments into a single working surface, the payoff for all that nervous waiting slowly started to arrive, one calibration image at a time. The first fully aligned test image, released publicly in early 2022, showed a single sharp star surrounded by a faint scattering of distant galaxies in the background, an image intended purely as an engineering test, not a scientific showpiece, and yet one that immediately demonstrated the mirror alignment had worked essentially perfectly. By July 2022, when NASA released Webb's first full set of science images to the public, that same careful engineering work behind the sunshield, the segmented mirror, and the deep space orbit at L2 had translated into observations that reached back further into the universe's past than any telescope before it. Faint, reddish smudges of light identified as galaxies that had formed within the first few 100 million years after the Big Bang. Their light stretched by billions of years of cosmic expansion into exactly the infrared wavelengths Webb was built specifically to detect. None of that would have been possible without the specific engineering choices traced through this entire story. The decision to prioritize infrared observation over visible light, which demanded extreme cold, the decision to achieve that cold with a tennis court-sized sunshield, which demanded a distant, stable orbit at L2, and the decision to build a mirror far larger than any rocket fairing could carry intact, which demanded 18 individual segments, folded for launch and unfolded, one careful motor at a time, in the cold and dark, while a room full of engineers in Baltimore held their breath and watched the telemetry come in.